Hello, welcome everybody in the next installment of the series The Ray Tracer Challenge by James Buck, where I am implementing chapter by chapter from the book The Ray Tracer Challenge in a language I've not used before, but I wanted to learn, Rust.
Hello, just a short intermission from a little bit wiser and older Jacob, which by now has done some of those recording sessions and some more streams, and has realized he forgot to tell you that there are information in the description below regarding the GitHub repository where you can get all the code we are writing here to follow essentially along. Furthermore, please bear with me while I'm still learning on how to present all the different things I'm doing currently during the recordings. I get better from recording to recording, from session to session, so please be a little bit patient. And now, back to the program. Have fun.
And yeah, we are doing this together, so you can follow me along and we will do this. This actually is a bonus episode, as we are not implementing the next chapter of the book here, but refactoring something we have done before. We have, in the last installment of the series, implemented a lot of different matrix functionality here. We have different structs which essentially provide us with mathematical implementations as well as data storage paths for a matrix which is a 2x2 matrix, a 3x3 and a 4x4 matrix. And in the meantime, I read up a little bit on generics because there is a lot of code here, for example this, which actually is kind of copy and pasted and could be more generic. Furthermore, we have this strict definition to use 64-bit floating points. And even though this runs and is quite okay, with the actual distinction that this method here might be better, this submatrix calculation. But nevertheless, it's quite okay from the implementation standpoint. It's not and it's not too complex. But I actually would love to, for one, get away from this strict handling of F64 and simply specify that we want a float value there, and the compiler actually can decide which precision we need based on which platform we are on. Another thing I would love to do is like maybe be able to kind of reuse some of this functionality here for all the different implementations. We will see how far we get with this because as far as I understood generics, we can't do a specific thing there, unfortunately, which would be great to even further compress this together. But we will see how this goes while we are doing it. So I've not worked with generics before. I've just read about them shortly before this recording, and I'm very eager to try things out. So I guess we are just jumping in. So yeah, let's start by converting, I guess, the 2x2 matrix, which is the simplest of all of them. So what I'm going to do is here taking this struct, I guess, and simply, yeah, more or less removing it. We still need this derive statement here for another struct now, which we simply call pub struct, and let's call it matrix essentially. And this matrix now takes a type argument, and this is quite new, a feature, a const. Let's call it D for dimension, for example, which is a U size. And now we should be able to have a data here, which is then an array of an array, which is of type T. And has a size of dimension, and as it is a square matrix, we have an array of an array with this dimension. And this already looks quite nice because there's nothing red here. So we need, of course, to now start and refactor all of this, but we have our struct now, which is quite nice. So essentially what we have now is a matrix of arbitrary values, type T here, an arbitrary value matrix of type T with a given size, square size essentially, of the value D, which is a new size. So the problem there is now that we want to somehow limit the data that can be put in the type T to be a float. So to be an F32 or an F64. So there is a slight problem there, because as far as I understood it, you cannot set the type as a condition. I cannot do something like, I want this to be an F64 or an F33. Something like this does not work in Rust, because you can only constrain this with traits. But there is no essential, no float trait in Rust. But there is a crate, some sort of module for Rust, which actually implements this stuff. And I guess it was called num traits. Yeah, there it is, num traits. So how do we actually install this? Can we install? No, that installs a Rust binary. Okay, I actually don't see this. So I guess we are maybe editing this file directly then, and just adding the dependency here. Seems to work. It even gets a green check. That's nice. Okay, so there we go. And now what we should be able to do is we should be able to import. Let's get rid of this console here. We should be able to import actually num traits, and there should now be a float trait. Yes, there is. So we can import this. And what we can do now is we can actually specify that we want to limit the type T here with a condition which says it has to be a float. So what we've essentially done now is we have said that this type T needs to be a float. If I understood this correctly, I could actually write float here, colon float here as well, and wouldn't need this, and it would exactly be the same semantically. But in all the examples I saw, I quite much liked this where, because we might have more than one restriction there. Like we might have a restriction of we want it to be a float, we want it to be some other trait, so or to fulfill some other condition there. So if I understand this correctly, we have now defined a matrix with this data where T has to be a float. D is a U size anyway, we specified this here, and this is, for example, we specified this here directly. I'm not sure if this, let's take a look, maybe we could do it in another way as well and could say U size here. No, doesn't seem to work. So constants need to be defined directly. So let's do this and let's remove this again. Okay, so now let's start by moving over this implementations to be a little bit more, yeah, generic, I guess. So what was the syntax for this? We defined that we want it to be from, yeah, from what actually? So we want it to be from a type of array, I guess then, which is T. yeah, essentially exactly the same as before, where we have the... Oh, we need to specify which type arguments we are using within this construct here. So it would be usize. And of course, we are implementing the TD variant now of this trait, and we are getting information from this array. And so let's do this with, we need to limit this to float as well, because otherwise the type is not working correctly. So now we are taking this data here as well as we specified above. So I guess like this. And now we need to return a new matrix, and actually the compiler should now, yes, the compiler should now automatically determine that we are returning a matrix here, which is self, and we have given it the information what we are implementing with the correct conditions here. And so it is actually saying to the system, this works. Until now, this works exactly as I hoped it would. Okay. So what we have now actually is a function from implementation, which works for any float data type with any dimensional matrix, which is actually quite nice. So we've already removed another part of all the different implementations. So let's go on and check where do we have Matrix2f as well the next time. Matrix2f, let's see. Okay, we have a new here. So I guess we are removing this implementation here and implementing it. Yeah, why not? Let's implement this here. So we have now an implementation with t const d usize, and is a this should be then a matrix TD. Yeah. Oh, we forgot the trait. So where T is a float, and then the new needs to return a matrix TD, of course. And yeah, how do we? Actually, we need this struct to be filled with zeros now. So instead of hard coding this, I guess we could do something like, there is this array initializer thing. So what is if I do something like this and D here? Shouldn't this actually work? So no, it does not work. What does it say? Come on. The trait bound is not satisfied. Why is there a 1 there? Is not implemented for matrix whatever is a usize. So why? Oh, there is a 1 because we forgot to put the D here. Okay, still not working, but now a different error. Expected type parameter T, found floating point number. Ah, okay. Yeah, that's something I guess I wrote about as well. So the problem here is now we cannot use a simple type here because this is a primitive float, but the system now has to match it against this this trait here, and the primitive values does actually fulfill this, or it does this, but we need to especially convert it kind of into this trait, because the native version implements this trait, but the system does not know it yet somehow. So I guess what we could do is something like T from, so we create a new version thereof, 0.0. Okay, this doesn't work as well. Oh yes, from gives us an option object back, so it might fail if it cannot be converted. So we need to actually unwrap this. unwrap on an option object does nothing more than, if I'm not mistaken, either returns us the result directly or it panics if, yeah. So returns the contained value or it panics. So if it couldn't do this conversion, which is exactly what we do here, because this cannot be determined at compile time, I guess. Not sure, but yeah. So somehow I don't like this. I think this flawed implemented num. And num actually is a system trait, so there should be, I've read about this as well, there should be a 0 there. Ah, this is a lot nicer. So I can simply tell the system to give me a 0. There is actually there is for each of the number types there is such an implementation which returns the usual things like 0 or 1, so the identity and stuff like that. So let's use this here. So yeah, great. So now we have a new which is actually arbitrarily. I like that. So let's go on and take the next Matrix2f function, which would be the index trait, I guess. So let's convert this one. So we need again a t and a const. Ah, come on, const d usize with an index. Yeah, which is specified by usize for the generic matrix TD. Exactly, where T is a float. Okay, so of course there is Matrix2f array. That's not correct anymore. We are now returning a TD array. Yeah. So, because this is the data type of one row of information within our generic matrix. Okay, so that was easy. So what is the next one? The next one is the mutation, the mutable index access. So let's implement this as well. So t const d usize index mode usize matrix no td then, and where t is a float. So that was easy then as well. Until now it's very nice. So now the next one is the fuzzy equality. Okay, let's take a look on how to convert this. So I guess we are doing this next. So we have again t const d usize. We want to implement fuzzy equality with a matrix of TD. So essentially we are comparing always the same matrices against each other, and it will return a matrix. No, for matrix TD. So comparison of a TD matrix with another TD matrix where T is a float. So let's do this. Yeah, of course you cannot find Matrix2f because this is now a TD matrix. No method found fuzzy equality for type T. Yes, this is the first time I guess we need to specify. I hope this is how it was, like just, fuzzy equality with self, I guess. Okay, but if we can do self, we can write it here as well to make it a little bit more readable. Okay, so now is can't we do this as well there? Yeah. So Mismatched types. Expected struct. What is this exactly? Expected struct matrix found type parameter t. Maybe the self is a problem. Maybe there needs to be td. Let me just checking if this is a problem here. Matrix td. So maybe. Okay, so we don't. We have now a mismatching found parameter type t. So so we have this. We have this with the constraint that we actually type t implements fuzzy equality. Wait. We do not want that type t implements fuzzy equality. We want the matrix, just a second, we want the matrix td to implement fuzzy equality with itself, I guess. So, oh, no, wait. We are comparing these values directly, so this actually is a type t. No. This was right. We don't want to comparing one matrix with another. We already have, and we want fuzzy equality with type t to be implemented. There we go. Oh, this was kind of wrong. We want to implement it with a type t, and then it is working, and then we can maybe do something like we want to implement it with for self, I guess. And now we could do something like specifying self here. Yes. So this works now, but it isn't actually right. So this would only work for matrices of type D with a dimension of 2, as we are only comparing two rows and 2 columns. So we need to generalize this. And now is something I'm not sure if it works. I would be happy if it does. I'm not sure if it works. Otherwise, we have to do it in a different way, which is a lot isn't that nice if I understood it correctly. So I want to do this in a generic way. So can I do, and this is the big question, I want to iterate for row in 0, 2, and the question is, can I do dimension here now? It seems to me I can, which would be awesome. So the compiler would create another function of those for each of the dimensions used. For column in 0 to D, because we have a square matrix. And then we are simply checking if self row column fuzzy not equals then other row column, we will return false. And otherwise, after all of these iterations, we know this is the same and we can return true. So we can remove this actually. If this works, I would be so happy. And it really seems to work, which would be awesome. But let's not let's wait until we really compiled this. So let's jump to the next. What have we here? Matrix implementation, the determinant. So let's implement this for our new structure as well. So how would we do this? I guess we would have a t const d u size here as well, and we have this for tu then with a t which is a float. Oh, there's where missing. Where? Let's format this. Why do I always, yeah, tu, but yeah. So, oh, now this one returns, of course, a t, not an hard-coded F64 anymore. And yeah, it would compile, but the problem is this is not the implementation of the determinant for any version, but only for the version where d is 2. And the question now is, and I fear if I've read correctly, there were only theoretical ideas about how to do this, but the system cannot do this yet. That we cannot do something like d is 2 here. No, we cannot. As I would expect, what we could do, if I've seen correctly, is we can put a 2 here. Wait, what? Okay, now I need to remove this thing here, because now we don't have it as variable anymore, and we are now creating a concrete implementation if this value is 2. So for the matrix of arbitrary float type t with a dimension of 2, this is correct, and this is the implementation. So if we would call it now for a dimension of 3, let's say, the compiler would tell us that it is not possible to do because it doesn't know how. So let's check, are there any more Matrix2fs? This is the implementation of the Matrix3f. It's just where we are using it. We are essentially instantiating all of this here. Okay, so I guess we can remove those 2 types as we are not using them anymore. And now just to check, I guess I'm defining a 2f matrix type as matrix. Yeah, let's define it as F64 2. I guess. And now let's see if this looks quite okay. Maybe? I don't see anything red here. Which is something yeah. Okay, let's try and run the tests. They are running. So we've essentially refactored our Matrix2f into a templated version, a generic version. I didn't think this would happen so easily and so... Okay. I guess then we will commence with doing the same thing for the Matrix3f. So we are removing the structure there because we already have one now. We have the generic structure defined, so we don't need it anymore. We can remove the from because we actually have already a from implemented in a generic way. So we have implemented new in a generic way. This can go as well. We have implemented index. We don't need this anymore. We have implemented the mutability index. We don't need this anymore as well. We have implemented the fuzzy equality here. Can go away as well. And then we have, no, this is Matrix4f, 3f. So now there is something new. Yeah, all those. So let's take all of those methods and functions we need to calculate the determinant in the end of the 3x3 matrix, which actually is a kind of a recursive reduction to a 2x2 and then multiplying and adding and subtracting all of the different stuff together there to get the determinant. So we need to implement this. Where do we, there it goes. So this would be implement t const d usize as a matrix td. Yeah, we will not try to make this nicer now. Maybe we can later. So this does actually return a matrix. Yeah, it something like, can we do something like d-1 here? Generic parameters may not be used in const operations. Cannot perform const operation using d. Then we cannot specify, unfortunately, we cannot specify this. So what we are doing here is now we are implementing it in a specific way for a float type. Oh, there's a where missing again. A float type, yeah, which then is here. It's now we know that it is we know it is the implementation for a 3x3 matrix, so it will return as 2x2 submatrix, which is okay then, I guess. And then why is this not working? Where's the problem here? Mismatch types expected. What? Expected F64 found type parameter T. Why is it expecting an F64 there? Oh. Because we have here Matrix2f new. What we need here is matrix. Do I do that? Do I do it like this? A two-dimensional. Okay. This is not how it is done. Maybe like this. Okay, how do I specify? Okay, like this. Okay, so I specify the type, and then the compiler knows which new generic it has to derive and use, I guess. So yeah, now the error is gone because now we have a matrix of the appropriate type T here and not F64 anymore, which we hard-coded in the Matrix2f type, which we are currently removing everywhere. So yeah, so now we should be able to implement the minor as well, I guess, for this. So it does not return F64 anymore. It returns T, and this should be everything we need to do there. So this should actually return T as well, and yeah, this should work as well. And the determinant of the matrix should return T as well. What is that? It is red. What is it? Cannot add T to F64. No implementation for F64 plus T. Why is there an F64? Oh, because we initialized it with F64. So what we want here is a 0, I guess. Yeah. So binary assignment operation plus equals cannot be applied to T. Cannot use plus equals on T. So is this actually where is this plus equals thingy implemented? Let's check. Rust. What was it? Binary assignment operation. Binary assignment. Is this an operator we can? We can overload assignment. There, add assign. So if we tell this one that we want where T implements add assign, which we must import, of course, this should work. It does. So because now the compiler knows that this operation is actually defined on this, or needs to be defined on T. So the trait needs to be defined on this template thingy t here for this system to for this function to even be compiled. So it knows that this works. I'm not 100% sure why it thinks that a float does not adhere to this. So we will see if this even works later on. Maybe we need to change this. I'm not sure. It might be that the compiler might give us the run for our money there later, but let's see. Okay, so now we have done this. Let's check for further Matrix3f usages. 3f. There's actually the usage inside the Matrix4f. It's used here in a test. So, okay, so we need to do the same thing as with this one. We are now just defining it as a matrix with a dimension of 3. But now we have actually, I guess, removed, oh, we can remove those, and we have removed completely now the Matrix2f. So let's remove this as well. And then let's check if this still compiles. Cargo test. Okay, it does not. Matrix2f? Didn't the compiler just tell me that we don't... Oh, it's inside the tests. Why doesn't it know that we need this inside the tests? That's interesting. But I guess we can simply... Let's check this out. It's always the from calls, and the compiler should know now with looking at the data structure which kind of matrix it is initializing there. So maybe it should be able to just do this. Yes, nice. That's really, I like that. So if I'm now just going ahead and replacing all Matrix2f with just matrix, it should be, let's actually replace this in the whole file. So yeah, let's try this again. I love that. That's really, really great. I like that. That's amazing. So we can get away, we can just put away all those different types, and we can just work with matrix then, and the compiler knows how to put all the stuff together and give us the right matrix. I love that. That's awesome. So let's go ahead and yeah, refactor this Matrix4f, I guess. So let's go and see Matrix4f. We are really in the flow today. So yeah, I can remove this struct. I can remove from, already implemented this. We can remove new, as we already implemented it. Oh, there's another function. So let's remove this one. We have the identity matrix now. So let's implement this, I guess. Oh, let's remove that there. And let's take this and move it in the vicinity of the new, because we want to do it, I guess, in the same way. So let's remove this, and let's remove this, and can we generalize this? I hope so. Let's see. So if we have a matrix TD as a result here, what is the identity matrix? The identity matrix is essentially a matrix with a diagonal of 1s, always. It is completely unimportant to us what dimensions it has. Even if it would be a 100 by 100 matrix, it could essentially satisfy this. Yeah, it should be able to satisfy this by just... Okay, so maybe we could implement something like fn diagonal. Let's call it diagonal, I guess, and it takes yeah, it takes value t, and it returns a new matrix td, and this one would let mut m, which be a new matrix then, which has zeros all over, and then it would, for as we know now that this is possible, for 0 to D, it would set the matrix. Oh, I need to specify I in. So it would set I to the value, I guess. And then we return M. Okay, so now we have a new function which can create a diagonal of an arbitrary value. So the identity then is just a matrix diagonal with T1. Oops, I guess. Okay. That was easy. So yeah, I'm still at odds with myself if I want to use something like self in those cases, or the longer I'm looking at this, I more and more don't like the self syntax there. But we are sometimes using self, sometimes the specific type. Okay. For now, let's just not worry about this and just go on. So let's have this index usize for Matrix4f. This is the index implementation, which is already handled by our generic. Now we have the mutable index implementation handled as well. Fuzzy equality handled as well. That's just great to just remove all this duplicate code. So matrix multiplication. We didn't implement this before, did we? So, but in a square matrix, we can actually implement matrix multiplication in a generic way. So why not do this? Yeah, I guess why not do this? So let's do this. Where do we have all our generic macros, no, not macros, implementations here, I guess. So let's put it here. And now let's implement it for T const d usize. Because matrix multiplication in a non-square matrix is not that trivial, but in a square matrix it is quite trivial. So it's a multiplication with another matrix of the same type and dimensions. So where of course T is a float. We need to ensure that. So where? So this is why it cannot format the code. So exactly. So now the output of this is a matrix TD. And we are getting another matrix TD as input. So now we are creating a new one, and we are not going from 1 to 4, but from 1 to D here, I guess. And now, okay, let me see. We actually need to tell the system that we need another iteration loop here, because essentially we want for each column and row of the target matrix, we want to, let me just think about this. Yeah, we are implementing, we are multiplying each value of the row of the first one with each value of the column of the second one, and we are adding them together. So what we need here is for I in this one does as well go from 0 to D, and then we can remove this. And we need M row column, because this is our result, and we want to add together the results of self, which has a locked. Wait a second, we want to go one row, so we are locking the row here. So we have this one, and we are multiplying this with other which has the I here then and gives here the column because we want to iterate the whole column there. Yeah. What is this? Cannot assign t to t. No implementation for t plus equals t. I see. No, I don't see. Oh. That is, we need this, there we go. We need this, what was it? Add a sign again. This should fix it. Yeah, it did. Okay, now we have a generalized matrix multiplication for square matrices. Nice. So next one, I guess, Matrix4f. This is actually the multiplication with a tuple. Yeah, this we cannot generalize because we only have 4-element tuples. So I guess, wait a second, where did we just, this is the matrix T, so let me go just below that, I guess. Yeah, there. So this one is now implemented for an arbitrary type. It multiplies a tuple for a matrix of type T4. So it can multiply, let's say this is where T float. So yeah, this is okay. So this should multiply where T is a float. So and this is only for a specific 4x4 matrix because we can only multiply those with our tuples. Yeah, that's okay, I guess. So what's wrong now here? What? Mismatched types. Expected F64 found type T. Is there any more information if I try to compile cargo build? Is there any more information if I try to compile this? Oh, holy shit, there are a lot more problems with that. Use of undeclared type, Matrix4f. Yeah, we haven't defined this one yet. So can you help type alias, similar, expected T found? Okay, there we are. There it would have expected a T, but has a F64. Why an F65? Okay, so it wants to multiply the parameterized generic T with a other X, and other X comes from a tuple, and tuple is not generic and does not take any floats. So, oh, yeah. Okay, so I guess we are refactoring tuple next to support the same float number trait we now have, but let's make this work for now. So can we are creating a new tuple here, so we actually need F64s here as a result. So we somehow need to coerce our type into the F64 variety. Either we need to convert those, or we need to just restrict this type to F64 for now, I guess. We could do this. Maybe we could do this by just type annotations need, oh yeah, now I have this is, don't need this anymore, and I'm not saying this needs to be a float. Okay, so let's add a to-do here. To-do refactor once generalize once tuple has been refactored to use float trait. Yeah, so I guess this is okay as well. So now we can multiply with a tuple. Let's check our next, what is that? Transpose. We definitely can transpose any, transpose any sort of matrix, so we can generalize this as well. Where did we put all of this stuff? It was up here somewhere, I guess. This is the multiplication. This is fuzzy equality. Did we have a place for this? What was another one we implemented, like identity, diagonal? All of those others were traits. Fuzzy equality, multiplication. Yeah, okay, so yeah, I guess then let's just put this, where do we put this? Let's put this down here, I guess, maybe. So this is a transpose on, which is a matrix, returns a matrix TD, same type, same size. So we are now creating a new one of those, and we are just doing this over the dimension. This should already do it. So nice. So let's search for the next Matrix4f. So yeah, this is actually now something we can again not generalize. So I guess let's implement this for a matrix. We can generalize it regarding the type, but not the matrix dimension. So let's do this where T is a float. So this matrix 3f should now become matrix T3. And this should actually work. Mismatching types, expected F64. Do we have hard-coded F64 in here somewhere? Ah, there we have. Missed that. So, yes, okay, so this is again T then. Why is there no what? T not implementation for plus. Wait a second. Here, there is no plus going on here. There is something. Cannot add a sign T to what? No implementation for. Oh! I guess this is essentially where I guess this is essentially where our decision to do this and add this add sign here is coming back to haunt us. So it seems that floats do not implement this, but can we just do determinant plus? Okay, so did we do this anywhere else? Add a sign. There we did this. So what is this? This is a multiplication. Let's remove it here as well, and let's just do an m row column plus there. So, and remove this one, and yeah, and I think we are golden now. Yeah, we can remove this one just to be on the safe side. Makes things easier, and I don't really care if I have to write it out or not. You could even argue that it is better readable. So what's the problem here? Mismatch types, expected F64, find T. So we are returning a minor, which is this one is returning T. Oh, it's the other way around. There needs to be a T. Yes. Oh, this is the same problem again. We are calculating the determinant of a. Yeah, and this is kind of, I don't really like this because 99% of this here is identical to the implementation with the three-dimensional matrix, but we actually have to somehow copy it because we can't do it this recursive way. Determinant, and yeah, this of course needs to be a type T then, but this is not possible then, so let's make a 0 here. Oh, type T, I guess. So yeah. And now there is is invertible, so no method named fuzzy not equals found for parameter T in the current scope method found in T. So we can do, I guess, where, wait, we need to just enforce, do we do it here or do we do it for everything? Would it even be, yeah, I guess, no, I guess for it only is limiting this implementation. So let's just say T needs to be fuzzy equality, I guess. Oh, and it needs one type argument, of course, with what? With T. Mismatched types expected type parameter T. Oh, it's the same problem again. Oh, can I do this with a reference? Yeah, I can get the, oh no, okay, that's nice. So now we have inverse, which is no, this is a matrix type TD then? No, type TD, type 4, like, I guess. Yeah. So if it's invertible, fuzzy is not satisfy the trait. Yeah, it needs the, this one needs the fuzzy trait then as well. So in order for this to work, this needs to implement the fuzzy equality trait as well. Oh, there's a, what did I do there? That is completely, I'm getting a little bit tired here. So fuzzy equality needs to be implemented on this one, and yeah, so we need a new matrix here, we need to get the determinant, we need to, that should all work. It does, so nice. Okay, so I guess this should now be unused code. And I'm not that sure, but I guess I have it still in the tests, the instantiation. So let's check. Yes. So let's remove that. Let's replace all Matrix4f with simple matrix calls, and let's do the same thing if we didn't do it yet for Matrix3f. Okay, let's reformat this file and let's run the tests. And they are all running. This is so awesome. Ladies and gentlemen, we have successfully refactored our matrix implementation to use generics. And isn't this, I really like this. Isn't this awesome? You can now just call, okay, give me a new matrix here. Here is my 4x4 data, and you don't even care about if it's a 4x4 matrix anymore. If I, of course, would do something like give the compiler here, for example, a 3x4 matrix by accident, it should tell me, yeah, that it cannot find anything that can actually instantiate this type. So it will simply tell me this does not work. You need to have this square here, which is really, I like this. It's awesome. So, and it should actually only let us call the corresponding functions here if we are using the right structures and stuff like that. So it now knows when to actually call which of the functions without us specifying a direct type here or a direct derivative of that. I love that. So okay, let's commit that. Git status, what we change here? Ah, yeah, we let's add cargo. We git CI. Let's just let's do this here properly. Edit what was it called? Num traits dependency. This crate does provide us with traits to implement more generic handling of number-like structures. For example, float instead of a direct F32 or F64. Git add source matrix, git ci. Refactored matrix implementations to use generics. Just because, I guess. So I really much like that. So are we now refactoring the... Should we refactor the vector as well, or the tuple, better said? We have a lot of functions here we need to adapt, but I would assume it would go quite quickly. Okay, let's quickly do this and let's see where we land with this. So if we simply have this one, struct tuple, which would now be a struct tuple t, where t is a float, and I forgot the where again, as always. So we need to import. No, we don't want matrix float there. This is just wrong. We need numtraits float. So yeah, let's. Oops, what did I do there? Let's just. Yeah, come on. So, can we format this? What is this with type annotations needed? Cannot infer type for type parameter t declared on struct tuple. Note cannot satisfy numtraits float. What? Why? What? How? Oh, because we haven't used it anywhere yet? Yeah. Of course it cannot do this then, because it doesn't even know what to do with it, so we cannot derive what kind of constraint there is on that. Okay, that makes perfect sense. So now we are implementing the tuple t for t where t is a float, I guess, and now we are just replacing all of those with t. So this should work, and okay, let's just do this by a regular expression. So let's just replace f64 by t here, and let's do it for this line. Let's do it for this line. Okay, what's the problem here? There is oh yes, of course, there needs to be a 1 here now, and there needs to be a 0 here now. Mismatched, I guess this needs to be a 1 as well then. Okay, so, oh, semicolon there, and T0 here. And now we have fuzzy equality. Yeah, we need to implement fuzzy equality then for a tuple of type T. So first of all, we need to implement it for a type T, and it needs to be the same type T. So this should be float here, I guess. And yeah, it does not only need to be fuzzy, T also needs to allow for fuzzy equality. If it does not, we have a problem there. So yeah, this is, I guess, this works out, I guess. So now we have the implementation for add. So add should be the same thing. We are adding two tuples together, both of type T, where T is a float. Come on. Yeah, this should work. So we can subtract those as well, and T should be a float. There's a where myth missing again. We have this negative operation. It's the same thing. It's just, okay, there is no target because it only works on itself. Okay, yeah, we need where t is a float. So let's do this there. We have a multiplication operation, same thing, where t is a float. So, the other one now isn't a T64, I guess, but a F64, but a T. We have the same thing here for division. So let's implement this for tuple T. And the trade bound T doesn't satisfy a float. Wait. Other is again a... The trade bound num float is not satisfied. Did I forget? I did forget where t is float. However, there is something wrong. I implemented it only for F64. I should have implemented it for T. Yeah. Okay, so what are we doing here? We have some certain math operations on tuples. Okay, let's implement them. Where T is a float. And we need, of course, to specify this type here because otherwise it doesn't know it. So the magnitude now returns a T. Works. This returns a T, I guess, and it takes a reference to a type T tuple. Yeah. This is then this thing with maybe there it makes a lot of sense to have the self reference there, because then it would know what kind of thingy we are working on here. So did we already refactor this? So it's that simple? Let's try and run the tests. Cargo test. Okay, we kind of made some mistakes. Where did we make some mistakes? Warning, build wait, where does this start? Try again. So cargo test. Oh, there is a lot of stuff seems to be broken. Missing generics for struct in matrix. That's interesting. So we broke, of course we broke things in matrix. We broke exactly the thing, I guess, we were hacking in here before. Nice one. So, so I guess we now can remove, we can now replace this with a T here. We can make this implementation generic then. We can tell it that we want to multiply with a tuple of type T, and we want this tuple, no, we want T to be a float. And we need a where, of course. What shortcut did I just... Okay, where. And then the output is, of course, a tuple of type T. And the other is a tuple of type T. No. Is the output a tuple of type T? Yeah, the output of a matrix tuple multiplication is another tuple. So, okay. This now is, let's try and cargo test. Okay, still defect. So where's the problem there? Mule has an incompatible type for trade source tuple rs. So let's take a look into this. What is this? There is a multiplication with not with T but with F64 enforced. Let's run the tests again. There is still something broke. There is a lot more broken now than before, but yeah, okay. Whoa, what did we do? Missing generics for struct ray tracer tuple chapter 1. Oh, of course. Now our executables are we need to yeah, I guess we now need to make those things here. Either we would need to now set this type here, like we need to specify which kind of tuples we would like there. Yeah, or I guess we would need to make this generic as well. I guess if we just make this generic, it will I guess choose the most appropriate one, the one which is for example the platform we are working on or something like that. Let's try this. Let's just make this. There needs to be some kind of derivative entry point there which it can then defer all the rest of. So let's maybe just tell the system that we want all these nice little thingies here, and we want it where t is a float. Does this even work? No. Oh, we need to import it. So yeah, but in this case I'm thinking we might even do it without the where. Are we? No, let's we have always done it with a where. Let's further do it with a where. I kind of like it this explicit. No idea if it's a best practice or not. So let's just do this. There is the next one. It's the it's the implementation. So now we need this implementation where t is a float. So the position is now a tuple t, and the velocity is a tuple t as well. So this should be all right. We have another implementation of an environment there, which is now an environment t, and it's where t is a float. So we do this for there and this and go on, and tick function. Oh, this function now. Yeah, how do we define? Let me just try if this works. Maybe. I have no idea if we are defining it like this. I'm just now guessing. And now can we say where t float? Woo! Yeah, cool, we can. So now we have this one and no more errors. So I guess we may be able to, let's see, can we run this one separately? Cargo run --bin chapter 1. Okay, it at least did some calculations. No idea if they are correct. We need to run the tests to see this one, but I guess everything's working. So let's do the same thing, and seeing this value, I guess it used the F64, which is the actual bit size of my processor and my registers here as well. So yeah, let's do the same thing here for the chapter 2 thing. Oh, I guess we can easily copy that over because it's the environment and those things are exactly the same. The tick function is a little bit different, so let's just copy this part and let's import float here as well. So that's a nice one. Let's do this tick environment then, and we need to, how did I do this? I guess like this. So let's do this and this and this, and let's say where t is a float, and from point to canvas. Oh, yeah, so I guess this one is taking then a t as well, and but it only is for this method then, or I guess it's an implementation with a Wait a second, can we do something like this? Can I say I want this t here and I want to be sure that t is a place where t is a float, and then I can use it like this. Can I do this? Can I now just say this and it will be applied to the parameter t is not constrained by the impl trait, self-type or predicate's unconstrained type parameter. Okay, I guess this is not going to work because now this pixel would need to be, yeah, but it isn't. So I don't care. Then let's do it another way. Let's do it like this. Let's do it like, we can simply say where t is a float here, and we can just parameterize or make this function to a generic. What is this? Non-primitive cast t as use size as an O. Oh. Okay, so it seems to me that we cannot so easily convert a float into a use size anymore. So let's do not an as use size, but a to use size without sweating this too much, if this works, maybe. Okay. So I guess we can easily see, because this is the okay, so implemented executable to render and show what? Mismatched types. What is mismatched types? Expected option found. I don't think this is what. Try using a variant of the expected enum. Some can with, but no. It should be, oh, is this returning an option? It's returning an option. So we need to do an unwrap there. Unwrap. Yes, nice. Okay, so, and now this maybe works. So let's first of all try cargo. Oh no, let's run, what was it? Bin chapter 2, I guess. It did a lot of calculations and then it wrote the output, and let's see. This looks right, I guess. It was the ballistics projectile render, so this seems to work, and these values here seem okay as well. So let's check cargo test. Compiles and works as well. Yeah, I guess we have successfully refactored the tuple as well, and removed this little bit of not so nice code there. So let's get it. So git add. Yeah, we actually need to do to add all of this in one commit. So because it all belongs together. No, source tuple git ci. Refactored tuple to use float, to use generics as well, to accept arbitrary float types. Nice, I like that. Yeah, not git push, git push. Let's push it, not push it. Yeah, so I guess we are done. So I'm kind of curious. It doesn't seem to select F64 by default now here, because I nowhere told this one that what kind of value this is, and it can essentially represent all of those values in F32 as well. So I guess it is just using the default register size, or the default architecture width of the processor, I guess. Maybe. So could we force it actually to use a different implementation? What would be if I introduce just one of those as an explicit F32, if I just say this is an environment, F32. So this should compile, but now it should actually have no choice but to use F32s throughout our chain. Matrices, vectors, everything. Let's try this. Cargo run bin chapter 02. Did it? I'm not 100% sure now because I don't have the comparison. Those values could be F32s or F64. Let's wait a second. Let's do a comparison here. Let's do this again and let's do it with yeah. Okay. You see they definitely have a larger precision. So if I enforce one of those, the compiler has no chance but to use those throughout. Let's take a look if the picture actually looks the same. I guess it does. I guess on a pixel scale we can see a difference. With a ray tracer, maybe later on, maybe we might see a difference. We will see. But we can definitely try this out then. I love it. I like it. That's amazing. I just like the fact that this is now completely decoupled from this internal representation. So yeah, and by default it's using the F64 obviously. I like it. I really much like it. So yeah, I'm very happy with the outcome today with our refactoring here, and thanks for joining us again in this refactoring session and doing this together with me, learning and finding out Rust. As I have promised, I'm getting better in Rust, and I'm learning and reading up on it in the meantimes when I have some time. And yeah, I hope that we might now go on a faster pace here. But you never know, because a lot of these things is just yeah, transferring all the things from the book into the implementation. Refactoring something like this is usually faster because I can work with code and stuff that is already there and that is already thought out in my head, like I would love to do it, or the basics of it. Like I, for example, learned again now how to multiply matrices together and stuff like that, because I haven't done it manually in I don't know how long, but now it's in my memory again, and I can easily access this. So thank you for again for joining me in this session, and I hope you had as much fun in this session with me as well. And I guess we will do some more of these additional and refactoring sessions quite regularly when we are moving forward in the book. The next session will of course be the next chapter again. So yeah, see you there and bye!